This video is going to focus on kinetic energy, its relationship to work, your intuitive feel about what has kinetic energy and how much, what determines kinetic energy, and maybe not most importantly, but kind of nuts and bolts wise, is how do we quantify the kinetic energy in an object? And there's two ways. So that's what this video is going to cover. Okay, first, let's remind ourselves of what is kinetic energy. And we all know that it is the energy of motion. And I'm going to say at the macroscopic level, that means like big picture, cars, baseballs, etc., all moving in an organized way, all going in a certain direction. That is what we call kinetic energy. There's another kind of energy of motion that is down at the microscopic level, and that's just atoms jiggling randomly in all different directions. And that's, you could say that's kinetic energy, but really we're going to say that's thermal energy. So this focuses all about kind of organized things moving in one direction. Cars moving, baseballs, humans, not the fact that when you put a ham in the oven, it starts to jiggle. That's called thermal energy. All right, you already have a lot of intuition about kinetic energy. For example, here we have two cars, and on the left we're going to say that the car is not moving, and in this one the car is going 30 miles per hour. That's maybe like 12 meters per second, something like that. Okay, so this guy is moving and the guy on the left is not. So why is this guy smiling and this guy is terrified? These cars are basically the same car, same color, same type of car, same structure. So we already know there's absolutely something fundamentally different about these two cars. And we know, you already know what it is that this car can't hurt anybody. I don't mean like the gas tank blowing up, that's chemical energy. I mean just the car sitting there can't hurt anybody, and this guy can really hurt bad, okay? And why is that? Well, because this guy has this guy has no kinetic energy, so it can do no work. So it can't do anything to this guy, and he knows it, so he's smiling. Well, this car is moving. And if it's moving, that means it has some kinetic energy. That means it can do work. And this guy, whether he's ever heard of kinetic energy, whether he's ever heard of this idea of work, force through a distance, he knows that moving cars can hurt you, and that means they can do work. Okay, all right, so that's it. You already have some intuition. More intuition about kinetic energy. Here we have two identical cars, and let's suppose that this guy is moving at 10 meters per second, and the same exact kind of car, this one is moving at 20 meters per second. And I'm just going to call this guy number 1 and this guy number 2. So over here, we're going to say, no surprise, is that the kinetic energy of car 1 is going to be more than the kinetic energy of car 2. So you already know that there's something about faster for identical objects means more kinetic energy. But how much more? That's a question that we're going to be able to answer here pretty soon. The other more intuition, suppose that I have 3 objects, a dump truck, a runner, and a kickball, and they're all going at 5 meters per second. Well, which one would you rather have, which one of these things would you like to have hit you head on, like in the head? Okay, yes, the correct answer is the kickball. It may not feel great, but it's not really going to hurt you. Why can't it hurt you? Well, let me call these guys 1 and 2 and 3, because we know that the kinetic energy of 1 is way more than the kinetic energy of the runner, which is way more than the kinetic energy of the kickball. So, not much Energy means not much ability to do work. So little force acting through a little distance on your head. It'll sting, sure, but it won't hurt. Okay, so that's the intuition. So what is involved here? Well, it tells me that mass must be a factor that will eventually go into kinetic energy. Because what we're going to do, we're going to develop a formula for kinetic energy. So I think mass probably needs to go in there. And speed, how fast something is going. Okay, and we're going to see that that's the case. All right, so the next goal on the next page is how do we quantify this energy of motion, this kinetic energy? We're going to talk about how do we quantify the kinetic energy that a moving object has. And it turns out there are two ways to know the kinetic energy in an object. And the first way you're already kind of familiar with, which is basically if you know the work done to make the object move, you know the kinetic energy. Okay. The other way to know the kinetic energy of an object is based on its mass and speed. Those are the two ways we can quantify the kinetic energy of an object. Let's look at way number one. All right, so what we have here is this is you, and you're looking at this cart. You have no idea what the mass is, but you see that it's not moving. So V initial is 0, and you can somehow, maybe your friend has a force sensor and your friend is saying, hey, I'm going to start pushing on this cart with a steady 100 newtons of force. And you are able to measure, maybe there's tape measure on the ground, but you know that he does that over 3 meters. So you're able to observe all that. And then later on, you look over here and you say, oh, the cart is now moving. Let's do red. The cart is now moving, and you don't know the mass and you don't know the velocity. So can we know the kinetic energy of the cart? And the answer is, of course we can, assuming no friction, which we're going to basically assume for quite a while here. All right, because you can quantify the work. And work is change in energy. And in this case, the work done was specifically, well, what it did was it made this thing go from not moving to moving. It didn't raise it up against gravity. It didn't squish it or stretch it. It just made it move. So that's going to be equal to the change in kinetic energy. And since you start out with the initial kinetic energy 0, you know that in this particular case, you know that in this particular case, the work that you do is going to be equal to the final kinetic energy because it started out with none, and you can quantify the work. So how much work was done here? Pretty easy, I think. 100 newtons acting over 3 meters is 300 joules of work. So what is the kinetic energy of this moving cart right here? It's going to be 300 joules. Okay, so did we know the mass? No. Did we know the speed? No. So we, in this case, knew the kinetic energy of the cart because we were able to quantify the work, which is energy transfer. All right, let's talk about way number 2. Way number 2 is, hey, you didn't see your friend. You don't know how much. Okay, here's what you see. You see this cart moving, and let's say that it's going at 5 meters per second. And you notice on the side of the cart, it says 10 kilograms. And so you have no idea. You don't know anything about the work done. You just weren't around to see it. All you see is this cart moving along, and you're wondering, hey, what's the kinetic energy of this moving cart? You know 2 pieces of information. You know the mass, and you know the speed. Is there a way that we can quantify the kinetic energy based on mass and speed? And the answer is yes. And it's called using the work kinetic energy theorem, which we're going to basically develop on the next page. We have a little bit of work to do and before we can start quantifying kinetic energy of an object based on its mass and its speed. So please join me on this derivation of, really it's the definition of kinetic energy. And it involves basically three things. We've got our definition of work. Hey, where's my cosine theta? Don't worry about it. In this case, we're just going to be pushing. Our force will be perfectly aligned with the distance moved vector. So cosine of theta is 1. We're also going to need our other equation that doesn't have time in an equation, and we're going to need Newton's second law, which isn't in here. So let's start with, okay, again, the goal here is quantify kinetic energy based on mass and speed. Well, here we go. Work equals force acting through a distance. Well, Newton's second law says well, what does it say? It says F equals ma. Remember, F equals ma. So I'm going to write this as ma for force times d. And then, because the parentheses don't change anything, I'm just going to go, I don't really need them, but I'm just going to switch the parentheses to go m times ad in parentheses. Okay, well where does that lead us? Well, now we're going to basically go over to our equation that doesn't have time in an equation. And let's start out by saying, okay, v squared, I'm going to make one little substitution here. So everything's the same. Now, I'm going to say instead of delta x, that's kind of what we use typically in our motion problems. We think of delta x and delta y, but I can rewrite that as d. And then now, do you see something that I see? There's AD and there's AD. So what we're going to do is we're going to rearrange this guy and solve it for AD and then plug it in. Okay, here we go. So I need to divide both sides by 2, multiply both sides by 1/2, fit that in there, 1/2, and that guy goes away. So I can see, I'm just going to write it, reverse the order. So AD is going to equal 1/2 V, I'm going to go ahead and write V final squared. That's V final squared. Oh, I still got to push that guy over. Forgot to do that. So minus, so you see that guy? He's on this side of the equation, so I forgot to push him over there. So V final squared minus V initial squared. And that's AD. So I'm going to substitute all of this into here. Okay, so work done is going to be m times 1/2. How do I do that? I'll just leave it that, and then parentheses v final squared minus v initial squared. Okay, so here we go. We're just going to say, you say, where's my kinetic energy? Well, it's coming here. The work you do, this is the work you do in making something speed up, is equal to 1/2 m parentheses v final squared minus v initial squared. And let's just take that one more step. Let's just what's the math, distribute or whatever, take the stuff out of the parentheses. So the work you do in making something speed up is equal to 1/2 m v final squared minus 1/2 m v initial squared. Okay, so we've got this guy right here. Well, what else do we know? We know that work is energy transfer. And in this particular case, if your work is being done to make something speed up, then work equals the change in the kinetic energy. So there's our second relationship. So what we're going to do is we're just going to combine these guys and say, there we go, say that change in kinetic energy is equal to 1/2 mv final squared minus 1/2 mv initial squared. And oh my gosh, that means this guy is your final kinetic energy, and this guy is your initial kinetic energy. And that means I can quantify the kinetic energy of an object based on 1/2 mv squared. So this is the definition, or how we quantify kinetic energy. And really what it's all based on, it's completely based on work. So the work you do in making something go from 0 to moving is equal to 1/2 mv squared. All right, let's do that let's look at that in a problem, and let's do a little example problem on the next page. Let's use our new definition of kinetic energy to solve an energy problem. In this scenario, I have this classic physics energy scenario. I have a spring, and I have a cart, and at the very beginning the spring is squished, and we know that means it has elastic potential energy in it, and the cart is not moving. Then some short time later we hear boing, and we turn back and we see that the spring is back to its natural state, meaning there's no energy in the spring. And now we see that the cart is moving at 10 meters per second. The mass is given. And I want to know, basically here's what I want to know is how much energy was in the spring. You say, well, I thought this was a question, I thought you were going to ask me about kinetic energy. Well, let's see where the energy was and where it went. And then you can see that the kinetic energy of the cart here is going to be equal to the kinetic energy, the elastic potential energy that was in the spring. Because where did the cart get its energy? The cart got its energy from the spring. The spring gave up its energy. You could say the spring did work pushing the cart, getting it to go from not moving to moving. The spring used its energy, its ability to do work, to make the cart go. And so if we know the kinetic energy, so here basically it is the kinetic energy of the cart is going to equal the spring energy in the spring, or the elastic potential energy. So this really is a, hey, what's the kinetic energy of the cart in disguise problem? All right, so let's just figure that out. So the kinetic energy of the cart can be quantified using 1/2 mv squared. So we're going to plug in, the mass is 5 kilograms, and the speed is 10 meters per second. We need to square that. And so what we're going to get is, that's 100, so there's 500, and half of that is 250 joules. So there's 250 joules of kinetic energy. Where'd that energy come from? It came from the energy in the spring. So that means we know that the elastic potential energy stored in the spring, basically it turned into, transformed, or transferred, doesn't matter at this point, but basically the energy in the spring became the kinetic energy of the cart, and that's 250 joules. So this is just one little example of how we can use our new definition of kinetic energy to answer energy problems. Bye.